Welcome back. My name is Yvonne Vermillion. I'm the president of the Dayton-Wright chapter of AFCEA, if you remember me from yesterday. I'm also the co-chair of this conference. I hope you're enjoying it today. What did you guys think about yesterday? Good? Great thing. And thank you very much, General Morris, for kicking us off today. I think that was a great way to open. Today you have the pleasure of having my vignettes live. So we're going to start that off today. In 1887, George Huffman, brother of Torrance Huffman of the Huffman Prairie, purchased the Davis Sewing Machine Company and soon after moved it to Dayton, Ohio. In 1892, the company decided to diversify and made their first bicycle called the Dayton. The bicycle sales were so successful that George's son, Horace Huffman, founded the Huffman Manufacturing Company to sell their bicycles under the Dayton brand. In 1949, Huffman created the Huffman Convertible, which was a children's bicycle with rear training wheels and footsteps. The invention of the training wheels revolutionized the market for children's bicycles and was the first Huffman bicycle sold under the Huffy brand. Now, let's hear from our next panel on how additive is revolutionizing the edge.
All right, thank you very much. So I'm Raleigh Dutton with Arctos. I work with Joe Shabika, and so I'm introducing a very stellar panel of rock stars in additive manufacturing. So what we're doing is I'm going to very quickly introduce them, and then I'm going to let them talk and tell them about their journey. So on our panel, to my immediate left is Dr. Mark Shaw, Director, Government Programs and Technology, GE Additive. To his left is Dr. Mark Benedict, AFRL, Additive Manufacturing Lead, and America Makes Chief Technical Advisor. To his left is Howard Cizik, Advanced Manufacturing Program Office in the Rapid Sustainment Office. And then on the end is Dr. Marilyn Gaska, Senior Fellow Research and Technology, Lockheed Martin. So if I can get the first chart up, please. All right, so I think everyone has seen the Gartner hype cycle. And I think what we want to do is there's not just one additive. There's many types of additive. And so with that, the panel we have has had different experiences across it. And I've asked them to, next chart, please. Next click. Tell them where they are. And then say, what's the pacing issue to get to the next part of the Gartner hype cycle? And then I want them to close with, next click, what's the next wave? Where are we going? So on that, let me turn it over first to Mark Shaw, GE Additive. Next click.
Thanks, Raleigh. Thank you for inviting me to talk about additive. I've been I'm one of the additive old timers, which means I've been doing this a decade. So in additive years, that's a really long time. So my journey started in March 2011 when I was hired to lead an engineering team for GE's next generation narrow body. We call it the LEAP engine, replaces the CFM, the world's most popular engine. I was asked to lead a team to develop a fuel nozzle. I have been a part designer for most of my career at GE Aviation. And quite honestly, I wasn't super excited about that ask, but I was asked by a vice president, so the answer was yes. He said it felt like we might be looking at some new technology, we don't know. That quickly turned into GE's and really the industry's first application of metal additive for airworthy applications. So we started on that journey. Along the way, we purchased a local company in Cincinnati called Morris Technology. That became our supply chain because there wasn't a supply chain. And so I put some dates here to kind of align at least with my journey and my experience. Somewhere along that innovation trigger, you see that slope of excitement, I'll call it. Up to peak of inflated expectation. There was a time in 2012 when GE purchased Morris Technologies. Actually, if you look at the stock at all of those similar service bureau companies, that triggered a combination of many other service bureaus being purchased. So I'd say 2012, when we were excited about the technology, we've had some experience. We were able to actually make the parts for the first time, put them on some test rigs, and thought this was the path to the future. So that's probably that 2012 date of peak of inflated expectation. Somewhere around 2013, as before the part was actually certified, but I'll say most of the development work was done on the GE side. We'd running engine tests and flight tests at that time, using a technology that had not ever been used in the past, where you know the story with additive. We combined 20 traditionally manufactured cast and forgings, which were brazed together into one single piece. We were very excited about what was happening in additive, but GE at that time, if I'm being quite honest, we kind of really didn't know what to do next. So the question was this additive technology just kind of a one and done? It was good for fuel nozzles, or maybe only for this particular part number fuel nozzle? Is this something that GE wanted to invest in the future? At that point, we were running into a lot of roadblocks, and let me maybe give an anecdote. If you've been on the additive journey, maybe you'll recognize this part of the journey. So we all want to crawl, walk, run with new technology. Additive definitely is new. There's a lot of unknowns. We don't know design practices. The manufacturing process may not be as stable as we'd like. We don't have material data, material standards. If you know anything about additive, you've heard all this before. So typically what companies do, maybe a little different than what GE did in this case, is we'll say, well, I'm going to look at all of the kind of parts that we're going to be able to print. And we look at large spreadsheets of parts, and in the end, we're going to say, you know what, we're going to print a bracket. And the reason we print a bracket is because the risk level is lower on a bracket, and it seems like let's do easy things first. And so we're into the manufacturing of our first bracket. Things are going well for a while, but maybe we run into some questions with the material data, again, the manufacturing process. Once we start making these, they don't all come out exactly the same. We don't know why. Parts, traditional brackets in my world were typically stamped out of sheet metal, so we normally pay for those with hundreds of dollars. And since this is a new additive technology and we're learning now, our parts are coming out and they're costing me thousands of dollars a piece. And so at some point, maybe it's a management change, or maybe it's just a realization of, now we're having to stand up a supply chain. We are having some technical challenges that we wouldn't have in a traditional way. Tell me again why we're spending all this money to print a bracket. And so many of people that I work with, their journey dies here. Their journey, because there really isn't a good business case, or at least it doesn't appear to be a good business case at that point in this trough of disillusionment. And I'll say GE was a bit there in 2013. And obviously we didn't do a bracket, we did a fuel nozzle, but we had the next question. So what helped us kind of get out of that, having the first part certified by the FAA, in 2014 was a really important part of that journey. We got through a lot of those technical problems with our first part. We had good material property data. We had a supply chain that was consistent. I spent a lot of time with the regulators before working with the military. That's probably where I met Raleigh many years ago, was at an FAA, Joint FAA Air Force conference. I probably personally spent 5 years talking to regulators about why we think this process is a good, acceptable process. So we started to come out of that, to that slope of enlightenment, as this is labeled. The other thing that happened in our business, and you'll see this sort of down the road, is on some of these other things where we started G9X. We made a decision as a company that this was a technology we were going to pursue. And I remember distinctly sitting in a meeting. There was me and my boss and one of our technical leaders, I think it was my lead engineer at the time. And we said, well, we're an engine company, not a fuel nozzle company. Like, if we're really serious about additive, we need to print full engine parts. And so our vice president at the time said, I will fund you. He gave us, some money, not a lot of money, but really he said, you have 18 months. From the time you start now, you need to demonstrate for me that you can print a jet engine, you can run it in a test cell, and it meets requirements. And so if my vice president was sitting here today, he would tell us that we did not meet his deadline because it was 18 months and 2 days. So we were able to fire that engine in the test cell. But even then, our technical leaders, so in our world, that's our chief engineers, our consulting engineers, our controlled title holders, they said, I will not, even this was a sponsored program by the vice president, I will not approve you to run this 3D printed jet engine in a test cell in Lynn, Massachusetts, unless we build a second cinder block wall on the outside. So GE did that. They sent everyone home, except for the people running. So I guess those were the people that were dispensable. So sent everyone home, except those people particularly running was on a weekend. And I'm telling this story because it was successful. It's metal, it ran, it worked, and met all the requirements. And that's really what fueled us and really pulled us out of that to that slope of enlightenment. So I'll tell you now that we've since certified the GE9X engine. There's over 300 additive parts on every copy. Over 200 of those are low pressure turbine blades. If you know anything about propulsion, turbine blades are not the easiest metallurgy to conquer. So we, kind of just stayed the course. We were committed to it. And I would say GE is now on this plateau of productivity. We have a catalyst engine, which is another commercial engine, so major engine structures being printed on the catalyst. It's a smaller engine. I can tell you we're doing this also in the military. We typically don't talk about that in public forums, but you all in this room probably know that there's a couple next generation engines that have significant additive content as well. So I think there's one more click.
One more click.
So the little dot that I didn't talk about is GE additive launch. So GE recognized that the industry wasn't moving fast enough. GE did what GE does, is they went and bought a couple more companies. So they bought Concept Laser, a laser bed powder fusion company, and RCAM, which is an electron beam powder bed company. And from that point forward, GE was originally investing in additive. When I sat in that conference room, said we need to run this on a jet engine, that was all GE for GE use. So we were making that investment. At the point we purchased these companies that manufacture product like machines that people want to buy. We became a company, GE Additive was born, and we became a company providing technology solutions. Somewhere in that transition, probably at the bottom of that second little bump, I recognized that what I had done for new make engines, so lighter, cheaper, higher thermal density and heat exchangers, more durable, reducing parts from 10, 20, in some cases hundreds of parts to one, all those things that are sort of like next generation, I recognized that Additive had another benefit, which was logistics. In fact, I even remember telling somebody that I said, I think Additive is primarily a logistics technology. This is coming from the design engineer who can tell you all the really cool things we can do with Additive. And why I raised that, because I heard a lot about sustainment issues and readiness, right? Maybe you've heard those words in the past. And Additive, what I recognize, is a toolless manufacturing. So in our supply chain, when we were making these parts for GE products, I had a machine that was qualified and certified to a given material, and I'm running across multiple part numbers across that machine, and there's no tools. I'm like, isn't that what we need for a sustainment reason? If I only had some sort of thing that could make parts from software, from a digital twin, and print it out. Now, we all know that there's second steps, there's post-processing and heat treatment, and there's other things that need to happen. But really, I believe the problems with forgings and casting were primarily with tooling and with the fact that no one, I think Melinda said up here, like no one wants to bid on a 2-part order or 1-part order. They want a 100-part order. Well, Additive doesn't care. right? Because I can print one part this day and a different part the next day, and there's no tooling cost and setup costs in between. So we started this program we call Pacer Edge with the Air Force. It started, I was actually able to go, I went to the Pentagon, was in Dr. Roper's office with our most senior military, Tony Mathis. If you know any of the GE people, he is our most senior military leader. He had a couple things he wanted to pitch to Dr. Roper. One was additive. I had 10 minutes to talk about additive. He said, yes, I want to go do that. Tony, would you license to me? I know you do this. I know you've got FAA certification. Will you license to me that know-how? And Tony said yes. Pacer Edge was born in that moment. A lot of execution through the RSO that occurred since then. Bottom line, what's happening today is within 12 months, we received our first contract March 2020. I probably need that dot in there. I can kind of see, maybe that's where that blue dot is we'll call that March 2020. In March 2020, there's another major world event that occurred that you remember, March 2020. So we sent everyone home, and we won our first contract with the Air Force. And we called everyone back to the factory to go make some parts. So within 12 months from contract, we were not only able to take a traditional casting that was in aluminum, print it in cobalt chrome at equal weight. If you know anything about density, we had to make the part 1/3 of the volume to make up for 3 times the density. We reached airworthiness approval. Mark came down, was part of that review team. I think, Howard, I don't know if you were in that room as well. Okay. So we went through this, and it became the first part to receive airworthiness approval, a metal additive part for airworthiness approval. Since then, we have 6 or 7 additional parts. So that part was done, I'll say, more traditionally. GE designed it. It's a GE part on GE parts list. But we knew going forward this was about organic manufacturing. We put machines at Tinker, and we want to provide all the tools to the government. So we're no longer a contractor at that point, or at least a parts supplier. We're a technology provider. So in these 6 parts, they are owned by the Air Force. They'll be on either Air Force TDPs, on Air Force drawings, Air Force blueprints, Air Force CAD data. I mean, we're doing a lot of the work because we have some smart people that know some stuff about additive, but we're really only partners. We created material data. We worked with Mark very closely and Howard very closely. So your specs and allowables are all Air Force owned data. You can do what you want. You can share with the Navy. You can share with the Army. And so we are very close to the first 2 U.S. government-owned parts. We're at the end. I think we're at TRL 6 or so on those programs, delivering the material data, delivering the technical data package. The machines are in place. We had a ribbon company at Tinker. So very soon, the first 4 parts were printed here in Cincinnati. All that technical data is going to be provided to Tinker.
That's a great segue to Mark Benedict. Mark, over to you.
Thank you. So I'm with the Air Force Research Lab. We lead, discover, develop, deliver. It's that discover and develop function that spend a lot of time on relative to additive manufacturing. Acting as the forward sensors for the Department of the Air Force to see what emerging technologies we need to invest in and shape to benefit our war fighters. Also do that for OSD through the American Makes National Manufacturing Innovation Institute. That said, I think that we were asked to look at this hype cycle and where we're at on that journey. And if I could get my first chart up, I'd say that, and click it one more time if you would. There you go. This is the industry's position in that plateau of productivity or entering that regime where we've identified the ways to standardize the work to get to airworthy quality. There are 3 parallel standards-based paths to what we feel is airworthy type parts, and those are SAE, NASA, and the American Welding Society's approaches. And so we're standardizing the work. It's becoming, I won't say commonplace, it's certainly transformative in the way that Mark Shaw was illustrating, but we're getting to that productivity plateau where it will become standard work, and we will realize the benefits thereof. The next wave that he kind of teed up there, and if you go to the next slide, this is kind of where the Air Force is at right now, and I think where the industry is starting to understand, great, we've got a standardized process. We've done all the work for qualification and certification. The realities in a you know, post-COVID environment, as General Morris alluded to, is, you know, where are we going to do this work? What's going to happen when we need to change rapidly to get inside our adversaries' decision loop and acquisition loops? That's undefined and unexplored to this point. So each one of these processes takes many years and many millions of dollars to get smart on, to establish, and, you know, that's all to the good to create the quality we need. But right now, we're going to start focusing resources on, okay, what's next? How do we get to the next wave? And it's great that we can print on one, maybe two different types of printers with 2 or 3 types of materials, but you can imagine that's such a small fraction of what we're going to be asked to do going forward. So we're really starting to make those investments and work with the standards organizations and bodies to define kind of how do we accept change, what can we leverage from prior investments, i.e. data, and how do we buy down risk and create those rapid qualification loops going forward. So that's kind of the next wave. Now, sitting in AFRL, I've got the, you know, personally I'm a technologist, so I enjoy this, the challenge of looking even farther out there. And I see there's a much bigger and third wave that will be coming. And, you know, to date, what the Air Force and a large part of the industry is focused on is part replacements. We have a design, we have a conventional manufacturing process, maybe it's casting, maybe it's forming, maybe it's machining, a lot of joining of the former processes. And we're going to replace that with additive, and it's going to save us time, it's going to save us money, give us some supply chain agility. But very little of the work at the, you know, in the industrial base is looking at using additive in ways that are truly disruptive, and what the Air Force is terming convergent manufacturing. So that's where you're integrating multiple advanced manufacturing processes with the digital design loops and creating a flexibility that is just going to change the way we develop and acquire systems. So if you go to the next slide. This is kind of a bold experiment in that direction, called Rocket Factory in a Box. This is where we've created a mobile factory in 5 Connex containers, complete with a, you know, design and development and control station to, you know, produce full-up solid rocket motors anywhere we can put those 5 Connex containers, which are fairly mobile and well situated. Now, the mobility really wasn't the desire here. It was our desire to push industry away from the you know, factories of monuments that are tens of $1 millions for each station in the development process. 100-acre factories where, you know, somewhere in the Southwest or you know, in a desert location, we've got a monolithic factory that is very slow to change, very slow to adapt, very hard to get development work into. Let's say we have a war event and we need to resupply. General Morris, you know, highlighted how challenging that can be to execute. You know, so this capability is right now out at Edwards, is working with simulants, not energetics. So we're still, you know, kind of a step away. But we are really integrating multiple solutions inside of this highly agile capability to do the design work, to look at rapid resupply, say. We can, you know, right now we can print about 12 AMRAAM sized solid rocket motors in a day. We're looking at accelerating that. We're printing, say, the casings and the windings as well. So it's not just the one process. There's post-processes involved in those and the integration of them. So it really is kind of this convergence of additive manufacturing with required post-processing and the design and control work that's needed to make that happen. And, you know, like I was highlighting, that's all part of this third wave where we're just climbing that slope of excitement, you know, heading towards peak expectations, and there's going to be a massive trough of disillusionment as we get to operational realities, and we're trying to get there a bit faster and do these bold experiments and see what that looks like. But you know, we're really advocating that the industry needs to move away from monolithic materials as drop-in part replacements, and while there's value in that, there's certainly much more value in creating parts that are designed for their application and their manufacturer, as opposed to just, legacy designs that are 50, 60, 70 years old that, were limited by the manufacturing processes at hand. Pass it off from there.
All right, that's a great handoff to Howard.
Next chart, please. Yeah, so I've been in the RSO now I was detailed there out of Air Force Mantech about 3 years ago. And so I've seen how the RSO has attacked this problem and worked with different folks to get this done. Actually, just want to mention that this was the 10-year anniversary of the establishment of America Makes, which is the manufacturing institute that Mark's heavily involved in, and that really was at the peak of this of our inflated inspections, just like Mark said, right? And when we started looking at this, the folks in LCMC said, there's a lot of work that needs to be done. And Ms. Nagai and her team established the ATTC at East River Road here in Dayton. It's run by UDRI, as well as a facility down in Middle Georgia, next to Robins Air Force Base. And they started working, basically saying, this is what we need to get done. We need to characterize the materials. We need to characterize how the machines operate. We need to figure out how to design, how to handle all this data that we're generating, whether it be the digital data that feeds into these machines to print the parts, or it's the data that comes out of the machines and that we use for design and to guiding our design things. And I think once they did this, they realized this is really going to be a lot of work. And so we've worked through that, though, over the last 6 or 7 years. We have had some successes in getting parts to fly. There's of course the metal parts that we've worked with GE on the Pacer Edge program, but there's also a long list of polymer parts that we've done, and there's little brackets and things that we've done to get on aircraft. We're still working through the scope of alignment. And actually, could you go ahead and click the next the build on this so we can see the next thing? And we're basically, for a lot of the metal stuff, we're working very closely with LCMC LP and Mark and his team to do metal parts. We're also working with the armaments group down at Eglin Air Force Base, which was mentioned earlier. They've taken on a massive undertaking to generate the digital data for their systems. And we're trying to take advantage of that. And actually, we've talked about digital and the data that feeds these systems. That's a huge problem for us because if it's a supply chain issue, often finding the drawing for that or whatever, we go back into GEDMix or wherever we have to go to find that, and they're just scans of scans, and it's really difficult to extract that information. And we often don't have all the information that we need to make some of the decisions that we'll have to make on these materials and the processes that we're going to use to make the parts. So we're fighting through we're fighting our way up the slope of enlightenment. We're learning a tremendous amount just by printing different materials and establishing the data sets that we're going to use for design. We have a lot of work left to do. And it's a lot of careful work that needs to be done. And I think one of the challenges that we're facing is that a lot of the initial work that was done, although we didn't know what we know now. And I like to say that additive still has to pay for all the sins of past technologies, right? So we have to get an understanding of really what it takes to make parts and to establish capabilities with additive.
Okay, thank you. Marilyn?
Okay, so you've seen that chart, but I'm just going to use some things I use for women in 3D printing in January that aligns my experience along that timeline. Because if you go to the next chart, hopefully, okay, in the next chart. So I was asked, after all this hype, figure out from Lockheed Martin perspective in corporate sustainment, what does this mean for sustainment? And about the same time in 2015, I was asked, or I volunteered with Ed Morris, the head of America Makes, the chair of the new Additive Manufacturing for Sustainment Working Group Advisory Group. I do not press the button on any additive machines. I work with all of this crew, and I know them. But the question, and I'm a systems person, what does this really take to make this successful? So because of that role, I was asked by AIA to work with someone else, which was Dr. Teresa Clement, who was the head of all the road mapping groups at the time with America Makes, to do an article on additive manufacturing as a sustainment enabler. And the picture I've included here, I think still holds, because it goes, and we've been hearing about the who, what, when, where, why, and how, but this is my view of what I had learned in that first year. And I am a software person that started in software CAD, so I understand 3D models, et cetera. I also understand business relationships and the IT that enables it in terms of the digital data. And so to go to the deployed contested logistics supply chain where all the hype was to print parts everywhere, it takes a lot of things to work together that aren't just the technology. And you have to have the model-based engineering, the digital thread, the security, and the business model and the lawyers. And if you can print it in a day and it takes you 6 months to put under contract, it's not agile, right? And we heard about that in terms of acquisition. So anyway, if you go to the next chart, we started then in America Makes after a meeting with Vice Admiral Cullum, who was a big Navy proponent of additive. A suggestion came up of, wouldn't you be able to run a business model war game to figure this out? And it shouldn't just be industry Lockheed, it should be an industry group overall. And so we said, okay, I'm the chair of the Maintenance Statement Advisory Group with America Makes. Let me ask them, like OSS, OSD. So the very first test one-day event was looking at the business model war game with a deployed focus, just in terms of contested logistics at the Center for Innovation for Lockheed. And we did 2 war games, and Deloitte helped run the first one. And then we started to have industry, government co-leads and figure out all the issues. And then we went from war games to workshops to solve the issues. And it went from sustainment to these are common issues for qual cert, et cetera, that are common across additive, not just sustainment specific. And then that aligned with the JAMWIG, which is OSD had set up. So if you care, and these charts become available, there are reports, and I put them all in it, that go along that timeline to click. Now, have we solved everything? No, not yet. Okay, this in June, with RSO support and participation, AFRL, et cetera, we had at MXD, the Manufacturing Times Digital, plus America Makes, plus the OSD, MXD, America Makes had the last workshop that the reports are coming out. And Agile Qual Cert is really key in terms of, the question I asked last year at the Aircraft Airworthiness Sustainment Conference to this airworthiness people, how do we maybe qualify something for less than 8,000 hours to say it could be good for 4,000 hours? And I found out there wasn't really a good answer, and we have to work through this together. Okay, so next chart. So I had put together this chart a few years ago, even to take this problem to ASTM for standards, because when you're looking at point of need application, whether at a depot or deployed or supply chain with DLA, everybody's out there and the articles are all out there, but the standards didn't really support this. And so this is just an example of a lot of articles that are out there of things going on. But I want to take this to today's world, next chart. Because now we have an additive manufacturing in the DoD instruction. And the paragraph there says, seek to use AM to support Joint Force commanders and the theater requirements, transforming maintenance operations and supply chains for increasing logistics resilience and improved self-sustainment and readiness for military services. So our challenge is how do we continue to do this and support the now instruction that we helped to shape with all these working groups and war games. Now they actually have put this as an instruction. And Army Project Convergence 21 did rapid manufacturing, advanced manufacturing on the battlefield, and there are articles out there. Air Force Expeditionary Centers, there are articles out there, and I just linked to everything. And Arctos, maybe I should, is that all capital? You have capabilities that we've discussed, and we've discussed the less than full life repairs and all those challenges. So I just leave that for questions and discussion.
All right, thank you very much. So while questions are coming in, let me go ahead and give the kind of a warm-up question. And I think everyone kind of touched pieces of this. How can we maximize the reuse of additive manufacturing or data? What are strategies to establish equivalence between parts made on different machines, scan strategies, sources of powder, et cetera? Marilyn, let's start with you.
Okay. Okay, I wasn't expecting the first start with me, but we can. Well, I mean, we need to be able to just make this go faster and figure out how this all comes together. So to do all this, I work within Lockheed with all the people that do all the additive, and we're really looking to make sure we're engaged in how to do this faster in terms of rapid qual cert, manufacturing to sustainment, but working in partnership with customer set to make sure we do it faster. I'll pass on to anyone else that wants to add.
Okay, Howard, you're next.
Yeah, look, we're still learning a lot about this. We know a lot about this. We have, experts like at GE Additive and other places. I think we're going to have to at some point, we're just going to have to sit down and start comparing data and looking at this. The Cognizant Engineering Authority are not going to sign off on something until they have data that supports their tenets and what they need to approve that. And that's simple. I mean, we're fighting that battle every week. We fight that battle with an engineer somewhere saying, he says, show me the data. So we're going to have to put that data together. It's going to have to be in a data that in a format that's in some ways traditional, and it's going to have to be it's going to have to apply specifically to the application that we're looking at. So I think that's our approach. I don't know how we're going to get past that until we get a lot more experience and a lot more use cases out there.
Mark Benedict?
So in 2021, we published a OSD level additive manufacturing strategy. One of the key pillars in that is competence. We've got to build the organic competence to understand what quality looks like with this process. And I think Howard referred to it as experience. I think that's exactly right. I think we have to, commit to keeping that experience and competence base alive within the Air Force, not only so that we can solve our own problems, but so we can work with partners in industry and understand what they're doing at a pace that really increases adoption.
Mark Shaw?
Yep, so I'll agree with everything my colleagues here say, but since I'm the mechanical engineer here in the group, I'll think about the NIAR presentation we saw on digital twin if you were here yesterday, and the need to modernize our technical data. So there's definitely, we start with what was there traditionally. It still has all the same requirements. So in a sense, we're reusing, or I'll just use the word modernize.
Mark, you must be psychic because the question came in and you get to start. For those of you that mentioned additive TDPs, what typically constitutes a sufficient TDP?
Oh boy. So let me just keep it kind of high level and basic, and we can talk the detailed technical offline. So one of my favorite sayings about metal additive is the best thing about metal additive is it's metal, right? I'm stating the obvious. So even Howard referred to this when he was talking about the fact that we're sometimes held to a higher standard. And what I always like to ask the question, if this were a casting or this were a forging, what would we do? So the question to the technical data package should be, honestly, it's no different. Now, obviously, I need a 3D file, which I might not have had for my casting and forging, so that part, I guess, is different. But with regard to the content, the way we've constructed our technical data package and provided them under Pacer Edge is those are machine agnostic. They are geometry, requirements, material data. You can use any machine, any supplier. Just like if I went to a cast vendor or a forge vendor, I'm providing technical requirements.
Thank you. Mark?
So I think that my experience with the Pacer Edge team is really opened my eyes in terms of what a tech data package actually looks like and maybe what it should look like. To me, the analysis really should be captured by the digital thread of newer tech data packages, because every time I try and move that part to a new machine, maybe there's a capability limitation, and I have to understand, can I accept that required modification? What are the stresses in that location? The requirements that we're working with now are, I won't say comical, but it's challenging, and we'll get a drawing off a TF-33 engine, moldy old paper from the 60s or something, And the requirements on that part are really hard to interpret. And it's certainly distilled down to that operational level of, I can't create the radius that is drawn in here. What do I need to do from a requirements standpoint in terms of how this part needs to be performed? So getting that digital thread involved with the tech data package to keep the requirements more actionable.
Yeah, I agree with everything Mark and Mark have said. I think the other side of this, or there's another challenge to this, is if we want to have distributed an organic industrial base that we're working with and working within, we're going to have, the Air Force is going to have to come up with ways to exchange that and pass those tech data packages back, address the issues of different machines at different locations, the qualification of those machines and other things like that. So there's another layer of challenges beyond just what's proper in a TDP. It's almost the logistics of getting those tech data packages to the right place and to those folks who can make the parts.
And ideally, we're figuring out how to work together with the OEMs and the supply chain and the services, that you're not starting from scratch to scan it because you can't get access to the original data. I mean, it should be figuring out the win-win in terms of a data as a service, all those kinds of things, which gets into the business model side. But it's also, if you go to the NIST model-based conferences, similar things are a problem in the supply chain, even with OEMs not giving the model to suppliers and people redrawing it. And I'll just go back to some of the things in discussions. Your functional testing still should be the same whether it's additive or not. And if you say it's additive, everybody throws in all these, you have to do all these special things. But what are the functional tests? Do we know what are the tests it has to pass? And don't make it too hard.
Okay, so let me start another question in the same vein. Start with you, Mark. What are strategies for selection of materials for printing parts for a specific application? Does the strategy involve data analytics approaches?
Yes, I like the term I heard yesterday as cobot. So I'm going to start adopting this idea of cobot, which is man and machine working together. So I often say part selection is not a spreadsheet exercise, but you do need spreadsheets. Right, so there's an engineering portion of whether we're talking about parts or materials. Illustration is, I gave you one illustration with the aluminum F-110 sump cover we printed in cobalt chrome. So there is this mapping that a human can do that says this part was made with this material, maybe because it was more adapted to castings. I can make it with this other material and meet the same technical requirements at the end of the day. So I think it is a cobot approach. Can't eliminate the human, but yes, I do want tools to help that human be more productive.
Right. Thank you, Mark.
So material selection is kind of a funny area for additive right now. It's on the order of, you can have any flavor you want of ice cream as long as it's chocolate or vanilla.
Or cobalt chrome.
Right, so we have two materials, cobalt chrome, nickel alloy 718, that are mature and that we can print with. Those are very capable materials that happen to print well. So we have to kind of look through that lens for virtually every part we see. We're maturing aluminums, we're maturing titanium, maybe steel at some point, but those aren't quite ready for production use yet. I think the bigger question is, when do we switch to creating materials that work well with the process, as opposed to this part used to be aluminum F357, so therefore we should print it out of aluminum F357. Moving to that more requirements-based definition and creating the material that meets that requirement in an optimal standpoint. That's when we kind of move towards that convergent manufacturing future, which is, again, probably about 2 waves out at this stage.
Yeah. Howard?
Yep. Actually, I don't have anything to add on the materials and selection of the materials. I think one of the biggest challenges, again, we go back to is just access to the original intent of the part, and how do we get there?
Carolyn?
And just picking up on that as an example, even with the American Makes Army AM now, we have figured out, as an example, how to license the junction box data, the TDP, so that all the supply chain could actually test and print that part, and they could test it for looking at supply chain validation, which brings us even into President Biden and the AM Forward, just in terms of making sure you're bringing the whole supply chain along. So that's the organic industrial base and the defense industrial base, to make sure we're working together so that we can really leverage all these technologies for lower life cycle costs and improve readiness.
Okay, so we have one last question, then we'll close out. So this will take you to the edge. Additive manufacturing is critical to extraterrestrial exploration, as there will be no manufacturing facilities on the moon, Mars, or in space in the near future. Please comment.
That sounds like an AFRL question to me.
I'm ready. So, yes, we concur. We're working closely with NASA on this question, and one of the I think relevant to this audience, one of the biggest rocks that we have to move and invest to do so is in autonomy. You're not going to have a technician there ready to do the process handoffs, to fix the machine when the machine breaks, to reset conditions, to do any of the material handling. You're going to have a level of autonomy and robustness that just doesn't exist today. We walk parts from one machine to the next. The operators are very involved, and the print might run 30 days for a really large part, and there might not be a lot of interaction during that time, but I'll guarantee you that every day that goes by, they're sweating a little bit of what they might have to jump in and to do to intervene and save 20 days of print time because it's starting to trend in a bad direction and things of that nature. So when we get beyond exquisite factories, which is where we're at with additive today for airworthy parts and safety impactful parts, that autonomy and that robustness is going to have to jump several orders of magnitude beyond where it is today. So we're going to have to make some massive investments in that area.
Yeah, I think the only thing I would add is we're going to have to think about physics too, because look, physics on the moon it's still gravity, but is that going to impact your powder bed builds, right? There are a lot of questions that we're going to have to answer and work through. And just again, logistics is another issue. How do you get all this material that you're going to need to make parts? How are you going to get back and forth, and is it worth doing it?
And we are doing some of that early work, right? So with NASA, they have a small metal printer on the Vomit Comet, if you're familiar with that modified airliner, where it's a vacuum-based electron beam printing system with a wire deposition feed, and have successfully printed good quality material. It turns out that the fluid is driven by surface tension, and that doesn't change whether you're in vacuum in 0G or not. So there is a future there. We're starting to explore the physics, and we're going to have to make decades-long investments in the autonomy and the robustness of the processes to trust them to do their jobs and pay the money to send them out to more austere locations than the shop floor.
Marilyn, you want
Just
to
to add, we do have a space business area with the Advanced Technology Center that's looking at all these things and working with NASA and trying to address these things. But a lot of times they don't think they do sustainment the same way as our business areas of Flightline. But actually, it's harder because of the autonomy. And so we can learn from them, and that may even accelerate other aspects if we figure this out for space in terms of making things more repeatable and autonomous for regular production. So just mention, if anybody cares, if the aircraft were at the sustainment conference, NASA had a 4-hour additive kind of what they do for processes, and they're offering them as best practices. So, and they're very involved with America Makes with Rick Russell.
All right, well, thank you very much. I think we're at time. Let's give our panel I believe we're at break. We're at 10-minute break.